Here we have a case where we have two plates which are mounted to the ceiling. From those two plates we are hanging a third plate which is joined to the two plates by a bolt. We have force F in here, and in this example we must calculate what is the maximum value for the force F when the material of this structure is Fe37 steel. And the maximum normal stress value for this steel is 147 megapascals, and the maximum shear stress value for this steel is 88 megapascals. And finally, we also have the maximum surface pressure value for the steel, which is 260 megapascals. So in this example, we must calculate normal stress, shear stress, and also surface pressure of the structure. So first thing here is that we are gonna start checking what is the maximum value which we can allow for the force F, and we must check if what is the maximum normal stress that this center plate can take, and what is the shear stress value which this bolt can take. So let's start by first doing a sketch about this middle plate. So we have this middle plate in here, like this, and we have a hole for the bolt in this middle plate, like so. And now when we calculate the maximum normal, when we calculate the normal stress on this plate, we must understand that when we have a normal stress case like this, and we have a hole through this plate, the cross-section area of this plate is smaller here where we have the hole. So if I draw here auxiliary plane, you will understand that. So along this plane in here, the cross-section area is reduced by the area which is taken away when there has been drilled a hole in here. So now the cross-section area for the shear stress is this plane in here. So let's start by calculating the cross-section area there. So the A sigma, which I named it, is the width of the plate 40 millimeters multiplied by the thickness of the plate, which was 10 millimeters multiplied by 10 millimeters, and from that we must reduce the amount of material which was taken away from the middle of here. So that amount is the thickness of the plate, 10 millimeters, multiplied by the diameter of the hole, which is 15 in here millimeters, multiplied by 15. And this gives us the value for the surface area in there is will be 250 square millimeters. Like that. So now when we calculate what is the maximum force which we can allow here, well, the equation for the surface for the normal stress is N divided by A. And now we know that what is the maximum, we know what is the cross-section area, we know what is the maximum allowed normal stress, and now we have to solve the force N. And from this equation we get that N is sigma, so maximum normal stress value was 147 megapascals, 147 megapascals multiplied by 250 square millimeters, and the maximum value is 36.75 kilonewtons. So the maximum normal force which we can apply to this steel plate will be 36.75 kilonewtons. Well, we don't yet know if the bolt which we're using here is capable of withstanding such load. So now next thing which we are gonna do is that we're gonna draw a free body diagram of this bolt which is holding the structure together. So we have the bolt in here. It goes through the hole in here, and this is the middle section there. So we have here force F, and then we have shear forces on both ends of this bolt. So V in both ends there and F in there. So when the sum of all forces in equals to 0, it means that the V is F divided by 2, like that. So V is F divided by 2. The shear stress equation was tau is V divided by A, in which the A is the cross-section diameter of this bolt. And now what we are calculating is that what is the maximum value for the V, or maximum value for the F. So from this equation we can now solve that the maximum shear stress value was 88 newtons per millimeters squared, which was given here in the task, 88, equals to V divided by the cross-section area of the bolt. So the diameter of the bolt was 15, so pi times radius squared millimeters squared, like that. And from this equation we can now solve that the V is 15.55 kilonewtons, and we previously solved here that the V is F divided by 2. So from here we can now solve that the F is 2 times V, which means that the F in this case will be 31.1 kilonewtons. So what this means is that the maximum allowable force that we can apply to this bolt is 31.1 kilonewtons. And now we can see that in this example the bolt is weaker than the plate is, which basically means that 31.1 kilonewtons is the maximum normal force, or maximum force which we can apply to this structure. Alright, so now we have checked what is the force. Now we still need to check for the shearing. So let's first take a look at the plate. So when we have a plate, like in this example, I draw it again in here. So when we have a plate like this, and we have a hole that goes through the plate like so. So now you can understand that we have force here. So on the top surface of this hole here, where we have the bolt going through, we have force in this direction. And now when we have force in here, we actually have a shear stress case in here. So we have a shear stress which is trying to shear away this bit of material. So you can imagine that if we did this hole too close to this top edge in here, what might actually happen is that instead of the bolt shearing, we might actually end up shearing this plate in here. So now that I've drawn here this example, we can easily draw a free body diagram of this case. So let's take that section there and let's draw a separate free body diagram of this case. So we have this chunk of material. It has a shear stress on the sides. We have a case like this. So now on these surfaces, on this surface here, and on this surface here, we have V and V. And in here, inside this hole, we have the F. Like that. And now the size of this piece of material, well, thickness of the plate was 10 millimeters, and now the height or distance of the hole, center of the hole from the top, is 20. So we can now calculate the cross-section area of these sides. So the shear in middle plate, and let's call it tau 3, so the middle plate is V divided by A3, and we call this area here is A3, like that. So in this case, the V value for V is F divided by 2. Quite simply, you can see it from the image. We have 2 V's and 1 F, so it has to be so that one of the V value for V is F divided by 2. And from there we can solve that the tau 3 is 31.1 10 power to 3 newtons. So this was the maximum value for the F, which we calculated. This divided by 2, and then that. Oops. Then that divided by the surface area into which this force is applied, which will be 20 millimeters multiplied by 10 millimeters. And from here we can solve that the shear stress value will be 77.8 megapascals. So the shear stress at this plate, at this middle plate, will be 77.8 megapascals. Well, finally, what we could now also do, we could also calculate the shear stress for these side plates. Okay, but I leave that to you, so you can check that one if you wish. And now we will still check for the surface pressure in this bolt in the middle of this plate. So the bolt was like so. Okay, so in this example, the force which is affecting this bolt, we have surface pressure force from top in here, FSP, and we have shear forces at the end, like so, supporting this one. So FSP is 2 times the shear force, which will be which will be 31.1 kilonewtons, and the projected area in here is this area of the pin, like so, or the bolt. So the length of the bolt, or the thickness of the middle plate, was 10 millimeters, and the diameter of the bolt was 15. So it will be the sigma SP will be 31.1 10 to power 3 newtons divided by the cross section, or the projected surface area, which will be 15 millimeters multiplied by 10 millimeters, which equals to 207.3 megapascals. So now we know that with the force of 31.1 kilonewtons, the shear stress value in the plate, or the shear stress or the surface pressure value in the bolt, does not exceed the maximum allowed value according to SFS 3200.